Now we want to generalize the chain rule for a vector function. Let's start with a simple situation when we have one real argument, just a single independent variable. And we compute sum A from x, the intermediate result, and then we apply the outer function and we compute fx, which is g at a at x. And we know that the derivative of f is g derivative times a derivative. And we want to generalize this, and fortunately, happily, the result will be absolutely the same, just f prime, g prime, and a prime will be Jacobi matrices of the partial derivatives. So, first step, imagine that we have not one but two intermediate results. Let's call it B or A1, A2. That means, given the input variable x, we compute A and B, and from these two, we compute the final result, which will be now f at ax bx. Let's consider some example. Say if ax is sine of x, if bx is x squared, then we and if g of ab is, say, a minus b, then the function will be g is the difference of the two arguments, and a is sine of x minus x squared. And we want to derive some rules how to compute the derivatives for general functions a, b, g, f without any particular function in mind. So if we start with the derivative, this is limit for h going to 0, f at x plus h minus fx divided by h. Now f is GAB. So we have limit for h going to 0, g at a at x plus h, b x plus h, minus g at ax alone and bx alone divided by h. And now we add and subtract one term here to arrive at limit for h going to 0. We copy the first, g at a x plus h, b x plus h, minus a new term, namely g at ax alone, bx plus h, plus, let me continue here, the same so that we don't change the value, g a x alone, b x plus h, so these two terms cancel each other, so they don't change the result, and we have to copy the last term, minus g at ax alone, bx alone divided by h. This is a similar trick as we used when we wanted to show how to compute the directional derivative. So notice that here is ax dx, the old point, and here a and b at the new point, x plus h, x plus h. And these new terms, ones with plus, ones with minus, are in ax only, and b at the new point, x plus h. Now, when we multiply this fraction, okay, I'll write it here at 1 second. So we have limit for h going to 0, and we have g a plus h, g at a at x plus h, b x plus h, minus g at a x alone, b x plus h. And now I divide and multiply by the following term: a x plus h minus ax times fraction a x plus h minus ax divided by h. And I do a similar operation with the remaining terms. So that will be g at a x b x plus h minus g at ax alone bx alone. And now I divide and multiply by b x plus h minus bx times b x plus h minus bx divided by h. Now when h goes to 0, then this fraction goes to, you see, yes, derivative of a and this fraction also resembles derivative, namely derivative of g. And here you see the second argument is constant and the first argument differs. And we divide by the difference of the first arguments. Well, this is not a very precise proof. We need one strong simplification. It's good to assume that the derivative of a exists and is different from 0. And then it's okay. So this fraction goes to the partial derivative of g with respect to the first argument. And similarly, this fraction goes to derivative of b with respect to x. And this fraction, again, resembles derivative. This time the first argument is the same, and the second argument changes. And we divide by the change of the second argument, which goes to 0 if h goes to 0. So this fraction goes to partial derivative of g with respect to the second argument b. Well, to conclude, we see that f derivative is sum of products of the derivatives, namely g with respect to the first argument times the first argument with respect to x plus the first derivative of g with respect to the second argument times dv dx. And this is the key point in generalizing the chain rule to vector functions? Well, you can imagine that if we have more intermediate results, like C, again that's C, then the same technique would arrive at a new term, derivative of G with respect to C times how C changes with X. You see, each term in this sum corresponds to one particular path from the very beginning to the very end. And the influence of these individual paths sums together. And each path consists of two factors, two expressions. dGdA is the strength of this dependence, and dAdx is the strength of this dependence. It may well happen that G does not depend on A. Then this arrow, this dependence, would have weight 0. If G does not depend on A, then this would be 0. Or it may well happen that A does not depend on X, then this would be 0. Well, and that was for one single independent variable X. But no problem to have more, say x1, x2, x3, x4, no problem to have more than one independent variable, the beginning values. And then we can consider the partial derivative with respect to x1, x2, x3, x4, and so on. So then we would replace this to partial derivative. And then, no problem to have, instead of one result, a vector as a result. We can have 2, 3 more functions, and we can do the same for every function. So we can have function f1, f2, f3, and so on. So as a result, we can write that the derivative of the ith function with respect to the jth independent variable can be written as a sum of products of the derivative of the outer function g and if we are interested in fi, then we consider the I G with respect to A, B, C, D, or A1, A2, A3. And K runs from runs over 1, 2, 3, the number of the intermediate results, times this derivative, which is the derivative of C when we differentiate it with respect to C, B, B, A, A. So the partial derivative of A sub K with respect to X sub J. And when we have, say, X from Rn, A from Rm, and F and G from, say, M and, say, P, then I is an integer between 1 and P. This is the number of functions. J runs from 1 to n. This is the number of arguments. And k runs from 1 to m. This is the number of intermediate results. Well, and if you remember the matrix multiplication, then this is exactly matrix multiplication. Sum of these terms, the scalar product of one row of the first matrix times one column of the second matrix. So we can write that the Jacobi matrix of the function f is the product of the Jacobi matrix of the function g times the Jacobi matrix of the function a, the inner function. Or if you like the prime notation, we arrive at something that was here. F prime is g prime times a prime, but prime means the Jacobi matrix of first order partial derivatives. Well, and in the next section we will illustrate this by some example.